Welcome to this educational video on pooling layers in convolutional neural networks, also known as CNNs. In deep learning and neural network architectures, CNNs are particularly powerful for image recognition and processing tasks. So, what exactly is a pooling layer? A pooling layer is a downsampling operation that reduces the spatial dimensions, width and height, of the input while preserving the most important information. Pooling layers serve several important functions in convolutional neural networks. First, they help reduce the computational load by decreasing the number of parameters. Second, they provide a form of translation invariance, making the network more robust to the position of features in the input. And third, they help in controlling overfitting by providing an abstracted form of the representation. Let's now look at the two most common types of pooling operations. The first one is max pooling. In max pooling, we divide the input into rectangular pooling regions and compute the maximum value for each region. This keeps the most prominent features in each region while discarding the rest. Let's see a simple example with a 4x4 input and a 2x2 max pooling filter with a stride of 2. Here, we take the maximum value from each 2x2 region to form our new, smaller feature map. Let's walk through how max pooling works step by step. First, we consider the top left 2x2 region of our input. We look for the maximum value in this region, which is 7. This 7 becomes the value in the top left of our output. Next, we move to the top right 2x2 region. The maximum here is 8. This goes into the top right of our output. For the bottom left region, the maximum is 9, which becomes the bottom left of our output. Finally, for the bottom right region, the maximum is 7, which goes in the bottom right of our output. And there we have it. Our input has been max pooled into a smaller feature map while preserving the most prominent features. Now, let's look at average pooling. In average pooling, instead of taking the maximum value, we compute the average mean of all the values in each pooling region. This provides a smoother downsampling as it takes all values into account. Let's use the same 4x4 input and 2x2 pooling regions to see how average pooling differs from max pooling. Let's go through the average pooling process step by step, just like we did with max pooling. We start with the top left 2x2 region. Here, we calculate the average of all four values, 1 plus 7 plus 5 plus 2, divided by 4, which equals 3.8. This becomes our top left output value. For the top right region, we calculate 3 plus 8 plus 6 plus 4, divided by 4, which equals 5.3. This goes in the top right of our output. For the bottom left region, the average is 9 plus 3 plus 6 plus 8, divided by 4, which equals 6.5. This becomes the bottom left output value. And finally, for the bottom right region, the average is 1 plus 2 plus 7 plus 4, divided by 4, which equals 3.5. This completes our output feature map. Notice how average pooling produces smoother values compared to max pooling, as it considers all values in the region rather than just the maximum. Now that we've seen both max pooling and average pooling in action, let's compare their key characteristics and use cases. Max pooling is excellent at preserving important features like edges, corners, and other distinctive patterns. It's generally more common in practice and works well for tasks that require the network to identify the presence of certain features regardless of their exact position. However, it can be sensitive to noise, as a single high value in a region, which might be noise, will be selected. Average pooling, on the other hand, considers all values in the region, which makes it better at preserving the spatial distribution of features. It tends to be smoother and less sensitive to noise, but it might not preserve important features as well as max pooling, especially if those features are represented by high activation values surrounded by lower ones. So, when should you use each type? Max pooling is often the default choice for most CNN architectures, especially for image classification tasks. Average pooling might be preferred in cases where the spatial distribution of features is important or when dealing with noisy data. To better understand the real-world impact of pooling layers, let's consider a practical example. Imagine we're building a CNN to recognize handwritten digits. Here's a simplified version of what happens when we apply pooling to such an image. On the left, we see the original image of the digit 5. In the middle, we see what happens after max pooling. Notice how it preserves the strong edges and distinctive features. On the right, we see the result after average pooling. It's smoother, but might lose some of the sharp features. Both types of pooling significantly reduce the spatial dimensions while retaining most of the important information needed for classification. This reduction in dimensions leads to faster computation, less overfitting, and often better generalization.